Good day. I am JM Subido, ID 120, and I'll be teaching ENGMEC3 LQ3. So the next problem is a problem involving a state of stress applied to an element. For illustration purposes, I'll be showing two different ways to solve this problem. First is using the transformation equations, and next up is using the Morse circle. So let's solve first using the transformation equations, but understand what the given entails. Let's draw our x and y plane here. So this is x and this is y. The 70 megapascals is being applied on the x-axis or along the x-axis, and it is a compressive force. Therefore, the normal force acting along the x-axis is negative 70 megapascals. Next off, we have our normal stress again applied to along the y-axis, and this is also a compressive force. Therefore, our sigma y is negative 90 megapascals. Lastly, focusing on this one, the arrow pointing upwards, which is parallel to the element, the rotation that is caused by this stress, or this is a shear stress, is negative or a counterclockwise direction. So this would be equal to tau xy, or the shear along xy plane is equal to, it's equal to negative 50 megapascals. And opposite it is also the same thing being applied. So uh it's 50 megapascals as well, but this time it's causing a positive shear, so it's causing it to go clockwise. Therefore, tau yx is equal to 50 megapascals because it is parallel to the x direction. So that's our second letter. Our first letter is where it is perpendicular to. So that's how you identify the parameters. So using the stress transformation equations, uh, using the stress transformation equations, the first principal stress, or the smaller one, is equal to sigma x plus sigma y over 2 minus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. So, well, we can use tau xy or tau yx. Since it will be squared, the value would still be positive naman. So, for the second one, it's just the same thing. So, let me just copy this. It's the same except for what I will be highlighting, which is this one. So, take note that the principal stresses only differ in terms of the sign of the second term. So, let's try to compute now. Sigma x is, again, negative 70. Sigma y is negative 90. Divide by 2. Minus the square root of sigma x is negative 70 minus negative 90 over 2 squared plus tau xy is negative 50 squared. So, let me fix this para buo. Then let's copy this also on the other the other principal stress, and let's just change the minus to a positive here. So the value that you would get here is your principal stress, which is the maximum and minimum normal stress that you can get. So uh using your calcu, you would be able to get a value of negative 130.99 megapascals for the first one. And then for the second one, you would be able to get a value of negative 29.01 megapascals. So that's for the first part. Then let's get the maximum shear in plane shear stress and angle of inclination of the principal planes. So for this, the transformation equation is T max is equal to just the second term of the principal stress equation. So it's just square root of quantity sigma x minus sigma y over 2 squared plus tau xy squared. So plugging in the values we got earlier, it's just negative 70 minus negative 90 over 2 squared plus negative 50 squared. So this would give us an answer of 50.99 megapascals. So that's it basically. Then we also need to get our angle. So since we want the angle, as stated here in the problem, the angle of inclination of the principal planes, what we will use is this equation. So tangent to theta p is equal to tau xy over sigma x minus sigma y over 2. So let's plug in our values and solve for theta p. Or let's convert it first so that it would be just instant solve. So theta p is equal to 1/2 of arctan tau xy over sigma x sigma y over 2. So that's the equation. So 1/2 arctan negative 50 over negative 70 minus negative 90 over 2. So plugging this in the calcu, the answer will be negative 39.35 degrees. So this means that it is 39.35 degrees counterclockwise from either the X or Y plane. So this means that if we want to represent the final answers, the principal stress one or the smaller one is negative 130.99 megapascals at 39.35 degrees counterclockwise from X plane, whereas sigma 2 is equal to negative 29.01 megapascals 39.35 degrees counterclockwise from our y-plane. So now let's try to solve it using Morse circle. Let's graph it first into our Morse circle. So let me just draw a circle here. We can convert our givens. So in this case, convert this one into 2 points with which are in the Morse circle. So the first point will be -70, -50. Yeah, and the next point will be -90, 50. So the points are x, tau xy. Pagsasamahin mo yung magkasama na same first letter. So here it's x. Then dun sa pangalawa naman, it's sigma y, tau yx. So going back, it would look like this. So assuming that this is the center. So yeah, it would look like this. Let's mark the center better. Let me just put marks here for the center. And then there. So again, this one is your -90, 50. Then this one here is your -70, -50. So how do we use the Morse circle? The rotation here is called your is called 2 theta. So it's the same here as well, based on our Morse circle. So that's for starters. Then our principal stresses are located here and here. So this is sigma 1, this is sigma 2. So our maximum shear stress is located here. This is tau max. And it's also located here. So this is negative tau max. We can use concepts of right triangles to get our values. So for this, let's first get our center, the center coordinate. So the center coordinate is just the midpoint of the two values or the two coordinates we had. And since the shear is just the same from both sides, it would just be at y is equal to 0. Let's just solve for the x value. So the center is equal to -90 plus -70 over 2. That's equal to -80. And take note that this value is also taken from the first component of your sigma 1 equation. So that's where it is derived from. Then our radius, what we can do here is draw, let me draw a right triangle here. So we know that this is r. Then the distance from here to here is -80 to -70, which is just 10. We also know the distance here actually, which is equal to 50. So we can use Pythagorean theorem since it's a right triangle. R is equal to square root of the square root of 10 squared plus 50 squared, which is just equal to 10 square root of 26 or 50.99 megapascals. So what we do is get our sigma 1, sigma 2, and tau max using this equation, these values. So sigma 1 is equal to C minus R, negative 80 minus 50.099, which is equal to negative 130.99 megapascals. Then sigma 2 is equal to C plus R, negative 80 plus 50.99 is equal to 29, negative 29.01 megapascals. Lastly, tau max is just equal to positive or negative radius, which is just equal to 50.99 megapascals. So those are the values that we got also earlier. And now let's get the angle. So using the same considerations, tangent of 2 theta is equal to uh opposite over adjacent, so it's equal to 50, yeah, 50 over 10. So it's just theta is equal to 1/2 arctan of 5, simplifying everything. And it will also yield a value of 39.35 degrees. So here, we also know that it's moving counterclockwise. So uh, here, the principal plane is counterclockwise. Wait. It has to move counterclockwise to reach the principal, from the original stress state that was given to reach the principal plane. So in retrospect, if you want to consider the principal plane going to the element given, you have to move it clockwise. So those are the values that you can get for this type of problem using the Morse circle. Thank you so much for watching. You may also avail syntax tutorials by scanning the QR code flashed on your screens. Once again, this is Jose Manuel Uisubido from Syntax, paving your way to excellence.